Welcome back. This is Mr. Erlin talking about similarity in right triangles. We're going to start with this idea that if I take a triangle like this, a right triangle, so if I take a right triangle and I drop from the right angle an altitude, making it perpendicular to the base, what happens is I end up producing three triangles. I have the biggest one, the papa bear, I have the medianest one, the mama bear, and I have the smallest one, the baby bear. They're all right triangles, and it turns out that they're all similar. How do we know they're all similar? Well, one of the theorems that proves triangle similarity is angle-angle similarity. So if I could demonstrate that all three triangles have at least two angles in common, then I know that these triangles are similar. And I could put in numbers like 20 degrees here and 70 degrees here, right? Because that would be a right triangle. Or this could be 30 and 60. But I usually try not to use specific numbers because we don't know what's actually going on. This could be 10 or it could be 12. So instead, I'm going to put something kind of like a variable. I'm going to put a little image in there. It's a star. And I'm just saying that this measure, whatever it is a star. It's a variable holding that place. Then we have a right angle, which we know is 90 degrees. And the third angle in the triangle, I'm going to mark with a little circle. And so what I'm saying is that star plus square plus circle equals 180 degrees. In other words, those three angles together make up a triangle. And we know that this right angle thing is 90, so that means that star plus the circle is equal to 90. Now, we've already talked about the big triangle. What I'm now going to look at is the medium-sized triangle, the mama bear. In this triangle, I've already got a star that's being shared, and I've already got the right angle that's being shared. So we know that the biggest triangle, having a star and a right angle and a circle, is now similar to the second triangle because it has a right angle and a star. So by angle-angle similarity, those are similar. And then I can look at the baby triangle, which has a circle in the corner and a right angle. So these two angles share these two angles. So in other words, this is similar to this is similar to this, therefore all three triangles are similar. Now, I need to be able to write the similarity statement. So it's easy when I have the star and the square and the triangles and the circles, because A is a star angle, goes down to the right angle, which is B, and then it goes to C, which is the circle. In my medium-sized triangle, I need to start it the same way. So I need to start at the star, which is A. I need to then go to the right angle, right? Because there's the right angle. So I go to the right angle, which is D, and then it means, well, yeah, that has to be a circle, right? Because they still add up to 180. And then in the smallest triangle, I need to start with the star. I've already got the right angle and the circle, so this must be the star up here. So I'm starting with B, and then I need to go to the right angle, D, and then the circle. So BDC. That's the triangle that's similar. We can do that same thing again here. Now it's oriented differently, right? Instead of it being right angle of the primary triangle pointed up, now it's pointed down. But the issue remains the same. I'm going to label this one star, circle, and right angle. And I'm going to label this one P is star, there's my right angle, and there's my circle. And in order to make it easy to come up with the similarity statements, I'm going to align them all the same way. So I'm going to put my stars in the top here and my circles in the bottom right. Now, when I look at my medium-sized triangle, I know that my P is already in my star spot. And then I go down, nope, I go this way. I come down to my S, which is my right angle. And then I go over to Q, which is where I'd have my little circle. In my small triangle, I don't have a star yet. I've got my right angle, my circle, which means my star has to go there. So Q is my star, going down to S for my right angle, and over to R. So if I'm saying PQR is PSQ, this one should be QSR. And that's how we write similarity statements for triangles. Now, having done this, we have the ability to find missing parts of the triangles. In this case, it's all about the altitude. And the trick is, when I'm looking at the altitude, that's SQ, that's this part, how do I figure out what that's related to? Well, it's here and it's here, isn't it? And so if I were to take this triangle and compare SR and PS, I would be able to create a proportion, right? I could say the orange is to the blue as the blue is to the yellow. So what is PS? Well, PS is the little partial there. That's not really going to help me, is it? Because I don't have the partials here. So I need to find a different way to get this thing involved. So let's see, what else do I have? Well, I know that this is the base there. And this is the hypotenuse, PQ. So I could do it like that. Could I say that SQ is to PQ? Let's see, SQ is to PQ, that's a whole side, as SR, that's a partial side, is to QR. That's not going to work either. Could I go SQ is to QR as PQ is to PR? Those are full segments. In other words, I want to get SQ, right? So I can say SQ is to PR as QR is to PR. Okay, what does that mean though? So SQ is this little part, and I'm going to say that that is to the hypotenuse of the medium triangle as QR, which is this long, the shorter side, is to its hypotenuse. Okay, so that's what I'm going after. I'm saying X is to 12 as 9 is to 15. Once I get it set up, that's the hardest part. Once I get it set up, I can cross multiply. 15x equals 9 times 12. 15x equals 108. X is equal to 108 divided by 15. 108 divided by 15 is equal to, actually it's exactly equal to 7.2 because it asks for the nearest hundredth. I'll call it 7.20. Now I need to do it again. So I'm going to say the little side is to the hypotenuse. The little side is to the hypotenuse. So I'm going to say X is to 21 as 11.2 is to 23.8. Cross multiply, 23.8x equals 11.2 times 21. So 23.8x equals 235.2 divided by 23.8. And I get x is approximately equal to 9.88235. Nearest hundredth, I'd say x is about 9.88. Another one. So again, I'm looking at the medium triangle. And I'm saying the short side is to the hypotenuse. So x is to 24. As in the biggest triangle, the short side is to the hypotenuse. As 7 is to 25. 25x equals 7 times 24. 25x equals 141.68. 24 times 7, 168. Divide by 25. 6.72. And again, that comes out precisely. I don't need to put squigglies in there. Okay, now, can we do that? Yes, they're similar triangles, so there's no reason we can't do that. But it turns out we've got a way that we can do this a little bit easier. So we do these problems the same way. I'm going to take x, the short leg is to its hypotenuse, x is to 21, as this short leg is to this hypotenuse, 11.2 is to 23.8. Cross multiply, multiply, divide, and solve. Similarly for this one, I'm going to take the short leg of the middle is to the hypotenuse, x is to 24, as the short leg of the biggest one is to its hypotenuse, 7 over 25. Cross multiply and solve. Now, these are cumbersome, right? The process of finding which parts match so that you can create the proportions is challenging. So I'm going to take you off on a little tangent for a second. I'm going to go talk about something we learned from algebra and probably arithmetic way back, the idea of the arithmetic mean or the average. We often think about it as the middle between 2 points, right? What's halfway between these two things? But really what's happening is we're saying to travel the distance from like the number 2 to the number 50 means that we have to take the distance that we have to travel. So it's 50 minus 2 is 48. That's the whole distance that we're going to travel to go between them. And we have to split it up. 48 divided by 2 is 24. And what we're saying is I'm going to take this and add 24 to get to this, leaving me with 26. And that leaves me with the ability to add 24 again, the same amount to get back up to 50. In other words, I'm splitting the journey into 2 parts. Now, turns out mathematically there's an easier way to do it rather than subtracting these 2 and dividing by 2 and then adding to the first one. We can do that simply by saying 2 plus 50 divide by 2. That's called the average. 52 over 2 gives me that same 26. Where does that come from? Well, if I've got 2 terms like A1 and A2, and I want to find the difference between them, that would be A2 minus A1. And then if you divided that by 2, that would give the distance. And then if you added that to A1, well, let's see, this is going to be the same as 2A1 over 2 plus A2 minus A1 over 2. They've got a common denominator, so I can call it 2A1 plus A2 minus A1 over 2. This is the same as this, so those are going to cancel, and I'm going to get A1 plus A2 over 2. That is where we get the arithmetic mean formula from. But today what we're going to be doing is talking about something called the geometric mean. And the geometric mean is similar, but it's kind of like on bonus caffeine drinks or something. In other words, we're saying that now to get from 2 to 50, I'm still interested in leaping to some number and then leaping to another number. But now instead of thinking about like walking half the distance where it's a linear process, now we're thinking more geometric or exponential in concept, right? The idea that it multiplies. So think about investing $2 in a stock and you want to get $50 and you want to find out when you're halfway there. Well, it's not going to be at $26. Instead, you're going to find that there's some multiple. You multiply your number 2 by some amount of earnings, and then you'll reach a middle point. And then when you multiply that by the same amount of earnings, that would get you up there. So it's the same idea, but instead of saying, let's subtract the 2 numbers and then divide by 2, we're going to divide the 2 numbers. We're going to say, if I need to get 250 from 2, I need to end up getting 25x, or I need to get 25 times my money. And now to split that up into 2 things, in order to make it multiply by 25 total, that means we have to find out what multiplies times itself to get 25, or the square root of that, which means we multiply times 5 here and times 5 there. 2 times 5 would give me $10. I'm halfway there. 10 times 5 would give me $50. So the geometric mean says to get from here to there and find this middle point, I'm going to take 2, not plus 50, 2 times 50. And then here we divided by 2 to say, what would the number have had to have been if it was the same number added together to make that total? Here we want to say, what would it take to have a number that multiplies together to make the same number as these two different numbers? Well, that's the square root. So for example, 2 times 50 is 100, square root of 100 is 10, and that's the geometric mean. Okay, kind of interesting, but so what? Well, let's put into our notes here first of all. The geometric mean of two positive numbers a and b, such that a over x equals x over b, where this is a consistent positive number. Then when I cross multiply, I get x squared equals a times b, which means x equals the square root of a times b. In other words, that's the way we find the geometric mean. So if I want to find the geometric mean between 6 and 30, I'll say 6 times 30 square rooted. In this case, we're doing simplified radicals, so I would treat this as 6 times. I would factor this one, 6 times 5. 6 has come out, and I get 6 square root of 5. That is the geometric mean between 6 and 30. Do it again. To find the geometric mean of these two, it's 16 times 28. I could multiply it out, get a big number, and then factor it, but I've already started the factoring, so I'm going to continue with this. 16 I know is 4 times 4, so why not leave those paired up? This is 7 times 4, but the 4 would then be left alone. I'm going to break the 4 into 2 times 2. The 4 comes out, the 2's come out, and the 7 stuck on the inside. The geometric mean of those two numbers is 8 root 7. Lastly, 12 times 50, 2 times 2 times 3 times 5 times 5 times 2. These 2's come out, these 5's come out, and the 3 and the 2 are stuck. That means 10 root 6 is the geometric mean. Okay, so what? How is that helpful? Well, turns out, let's do a little derivation here. If I go back to my triangles, I write triangle, and I drop my altitude, making my 2 additional similar right triangles. And I label these A, B, and C. And then I label these X, Y, and H. Now all my parts are labeled together. What I want to do is do that similar breakout, like we did before with Papa Bear, Mama Bear, and Baby Bear. And I want to orient them the same way so that I've got my similarity lined up. A is my shorter side, and I've specifically drawn this so that there is a shorter side evident. A, B, C there. Medium one is H, Y, B, H, Y, B, and the smallest one is X, H, A. So if I want to solve for something with H, I'm going to need to create a proportion using both those H's. Well, I've got 2 triangles that are similar here. Therefore, I need to find corresponding parts like X and H, and corresponding parts here like H and Y. Once I identify those, I can say that Y is to H as H is to X. Cross multiply, H squared equals XY, which means H is equal to the square root of XY. In other words, H is the geometric mean of X and Y. Let's do it again. What else could I find? Well, how about B? There's 2 B's. So let's see, this is the hypotenuse, so I'm going to need to get this one involved. This one's on the left side, so I'm going to need to get that one involved. So B is to C as Y is to B. Cross multiplied, B squared equals Y times C. So B is equal to square root of Y times C. Again, B is the square root of 2 different sides. Lastly, let's do A. So let's take A and A. Now we're dealing with these 2 triangles. A is the hypotenuse, so I'm going to need C. A is the bottom one, so I'm going to need x. So here I can say c is to a as a is to x. Cross multiply, a squared equals x times c. A equals square root of x times c. So all three of these sides can be found as the geometric mean of different sides. So yeah, we can just put those into our notes here, and I'll show you to add them into the notes here. What I said is that I've got this flipped actually. A is a geometric mean between x and c, B is the geometric mean between y and c, and H is a geometric mean between x and y. And sure, you can just use this as a cheat sheet or guide notes, or I can give you a different way to think about this. Now, I'd like to visualize that it's all about this little square up here, the right angle where we begin. That's the beginning of everything. And from that, there's three paths out. Again, from the right angle of the biggest triangle, there's three paths out. You can go down the right side, you can go down the middle, or you can go down the left side. If I go down the right side, when I do that, notice that I end up down here, this little point. And what I want to now look for is what other two segments come to that same point. Well, my segment X comes to that same point, and my segment C comes to that same point. So in other words, I can say that A, because it comes to this point, is the geometric mean of X and C, which is what we said right here. What if I didn't go down that path? What if instead I had chosen to go down path B? I'm going to color it yellow, but then I'm going to change it by putting blue on top so it makes green. Because you know that blue and yellow make green. So when I come down this B, I arrive down here at the corner. And now I'm saying that B is the geometric mean of the two segments that end here. Well, we've already got C. We see that C ends there. We see that Y also ends there. So B is the geometric mean of Y and C. B is the geometric mean of Y and C. And lastly, if I come down through the center through H, I end up at this point right here. And although C does pass through that point, it doesn't stop there. It doesn't have an end point. So H is the geometric mean of Y that ends there and X that ends there. H is the geometric mean of X and Y. And if you draw it like this, it's also color coordinated. Green is made from blue and yellow. Orange is made from red and yellow. And purple is made from blue and red. Screenshot of that if you wish. So we can use that here. In other words, if I wanted to find this length, if I wanted to find length AB coming out of this central corner angle here. No, excuse me, I'm looking for the altitude. So if I want to find BD coming straight down there, I need to go to the bottom of that to point D and find out what other segments end in D. Well, BD would then be the square root of AD times CD, the other two segments that end at point D. What that means is for this problem, I could say that coming out of this orange X, the orange corner, I go along X, landing there. X equals square root of 8 times 12. X equals square root of 96. So X is about equal to 9.80. 0. Again here, coming out of this right angle, I'm going down x. So I know it's x equals. When I get there, I'm going to go this side and this side. So it's the square root of 5, this side, and this side. But I know the whole is 37. This part's 5, so this part here must be 37 minus 5, which is 32. So x is the geometric mean between 5 and 32, which means x equals square root of 160, which means x is about equal to 12.65. Okay, same idea here. We're coming out of this square there. This time it's the 18 that's there. So that tells me that 18 is the geometric mean of the two that end on either side. So x times 15 square rooted. This one has a little bit different solving process. I don't have to just plug it into a calculator. Instead, I have to solve for x. So I have to get rid of this square root symbol. The way I'll do that is I'll square it. If I square both sides, I'll get 324 is equal to just 15 times x, clearing out the square root. And then if I divide by 15, I get that x equals 21.60. Okay, next one. Again, look for that right angle in the biggest triangle. Coming out of there is 21. So 21 equals. When I get to the bottom, it tells me what I'm matching with. Square root of 30 times, well, let's see, if the whole length is x and used up 30, then this is x minus 30 for that part. So 21 is the geometric mean between those two parts. Again, I've got the square root there, so I'm going to have to square both sides. 21 squared is 441. This will now just distribute through. Add 900. 1341 equals 30x. Divide by 30. X equals 44.70. Now, all of these were the same, right? They were all dealing with the altitude. So now we're going to talk about the leg. And there's two ways this could happen. We could be talking about leg AB. Notice that it ends at A, so we need the segments that have A in them, like AD and AC. Or we could be looking at BC. And since C is the end point, we expect this to be the geometric mean for the ones that end in C. All right. So here, if I want this side, x, there's my ending point. So x is the geometric mean between 24 and this whole thing, which would be 24 plus 2 is 26. Square root of 624. We're rounding here, so x is approximately equal to 24.98. Next one here, so we're coming down this side to go there, so x equals square root of, well, whole length is 12, that's one we want, but then we want this little part. If that's 12 and that's 7, 12 minus 7 is equal to 5. So this one is 5, that one is 12. Okay, so x equals square root of 60. So x is equal to 7.75 approximately. All right, number 14. These are getting a little more challenging. I have to pick whether to solve for x or y or z first. I got to find all of them. But if I found z, again, we're always thinking about this little right angle in the corner to start with. I could come out z, arriving there, and then I'd need this piece and the whole piece. Well, the whole piece is x. So z and x in the same equation, that's not going to help me. I could go y, that would give me 24, but how long is this piece? Well, if the whole length is x, this part is x minus 24. So again, if I did y, I'd have square root of 24 times x minus 24. That's two variables in one equation. That's not going to help me. But if I go down 27, I end up there, and I need the 24 segment and the x segment. That works great. So 27 equals square root of 24 times x. The x is under a square root sign. I got to get rid of that by squaring. 7 squared is 729 equals 24 times x. Divide by 24, and I get x is equal to 30.375. Now, I'm not going to round it off. Even though it says round to the nearest hundredth, I wrote all this out because this is the comprehensive number. It's the complete precise number. And that tells me that this x is 30.375. What I don't want to do is lose the precision early on in the problem. Eventually, it's okay. I'm going to round it off at the end, but I don't want to round it off too early. So this part that I said is x minus 24 now is 30.375 minus 24, which means 6.375. So this is that chunk there. So when I want to find y, I'm going to say y equals square root of 24 times this, which I just found is 6.375. So that's y is equal to square root of 153. So y is approximately equal to 12.37. So now I've got x. Well, I should have taken that further, shouldn't I? Because I should have said that x is equal to 30.38 rounded. Now I got to find z. So z is equal to the square root of what parts? This little part, 6.375, and this big part, 30.375. 6.375 times 30.375. So z equals the square root of 193.640625. Again, I'm keeping all those decimals for now, so that when I do the square root, I get only one rounding. If I rounded that too early, my answer would be off. Okay. Let's try it over here. So if I go to y, I'm going to have y is equal to square root of 20 times 20 plus x. That gives me two variables. If I do z, it gives me z is equal to square root of x times x plus 20. Nope, that's too much, but I'll use the 8. So 8 equals square root of 20 and x. Square both sides. 64 equals 20 times x. Divide by 20. I get 3.2 equals x. Add a 0 in to show it's precise because it says round nearest 100th. Now let's do y. So we know this is 3.2. So we can do y. Y is equal to square root of 20 times this plus this, so 23.2. So y equals square root of 464. Y is about 21.54. Lastly, z. Z equals the square root of the first little part here, 3.2, times the whole side, so 23.2. So that means z equals square root of 74.24. Z is about equal to 8.62. Okay, that gives us all the problems we need to do. To solve these ones, we'll just crank through it real quick. So this is a leg. It ends there. So I'm going to need this whole chunk. 36 plus 64 equals 100. So x equals square root, we're doing simplest radical form. 36 times 100. So I want to simplify that. 36 is 6 times 6, 100 is 10 times 10. So the answer is 6 times 10 is 60. So this one, x is coming down to 9 on this side, 16 on this side. I want simplest radical form, so I have to factor. Looking for nice pairs, and I'm getting them. 12. All right, this time 48 is in that spot. It's going to equal the geometric mean of these. So 48 equals the geometric mean of 36 times x. Square both sides. 2304 equals 36x. Divide by 36, divide by 36, 64 equals x. Okay, this is a leg, so I'm going to say 15 is equal to the segment touching it there, and the whole segment. This one's a square root, so square both sides to get at the x. So 225 equals 9x. So 25 equals x. This one is coming up the middle, so it's got 9 on this side. That's okay, but this side I need to get clean. If x is the whole length, but we're taking 9 away from it, this part is x minus 9. So 12 equals square root of 9 times x minus 9. I have to square both sides to get at that x. So 144 equals 9x minus 81. Add 81 to both sides. 225 equals 9x. So x equals 25 again. Last one is the leg. So I'm going to say 60 equals square root of this part, 36, and then this whole part, x plus 36. I'm going to square both sides. I'm going to leave it as 60 times 60. 36x plus 36 times 36. I guess I gotta take that anyway. So this would be 2304, which is this minus that, equals 36x. Divide by 36, divide by 36, so x equals 64. Thanks very much. Hope you enjoyed working with similar right triangles and the geometric mean.